Good morning, class. So as you know, we have entered into the topic of exponential growth and decay. And it's very useful in analyzing populations, in analyzing interest if you're investing in how much you will earn after a certain while, depending on what the rate is, and on other factors like that involve decay, like radioactive decay of an element, depending on its half-life, how much it is. So we're going to look at that using a program called Desmos. So we go on Google and type in desmos.com. And it's a very useful online, free math graph and calculator program. So if you look, people have done projects before and they came out nice, and it's very useful for analyzing behaviors. So as we know, you click launch calculator and we got to this page, and we see a grid over here, and on the sidebar you see this is where you type your equations, restrictions, and so on. So as we know, I have stated before that the standard equation for exponential growth is A equals P 1 plus R to the T, where A is your final quantity. If it's population, your final population. If it's investments, it's your final total amount of initial money with money earned, depending on the interest rate. So, and P is your initial amount, population of rabbits in society or something like that, or it's your initial amount invested. Over here, R is your rate in depending on what, like if it's rabbit population starting off, you would say that in a year maybe rabbits double or triple depending on what their their gestation period is and all that. But I think the actual number for rabbits may be somewhere larger than that, way larger, because they reproduce fast. So R would be a larger number. So if R was 0, then that means that there is no rate of change. So there is no anything being added or taken away, because 0 you would have inside being 1, and no matter what the time elapsed is, it would always, your initial amount will stay the initial amount. And T, of course, is time in years. So we're going to be using that on this graph, and we may have to shift other things a little bit here. So instead of A, we will have A be Y, in which our Y component of the graph will be our final amount. P would stay the same. R we will change to C due to the fact that Desmos has R for radius, and we're not using that today. And T, Desmos doesn't, unless it's X, it doesn't acknowledge it as, a variable in the X-axis. So we're going to switch that to X. So keeping that in mind, you see that down here we have these things called sliders, and we're going to use them actually to analyze the behavior. So starting off, we see over here, given that our P in this case, so let's talk about rabbit population. P is 1, so we at the 0, where X is 0, that's at the 0th year, that's at the starting point. Our starting population is 1, so 1 rabbit. But in our cases, we will actually make it be 2, because 1 rabbit cannot procreate with itself. So we'll have male and female rabbits to start off with. And C, our rate, would be, in this case, if we leave C to be 1, we look up here and we see 1 plus 1 is 2. So that would mean that the population would double. So let's say for every year passed, the population doubles. So, the initial 2 rabbits create a litter of 2 more rabbits. So we see over here at the initial year, our start was at 0th year, we have 2 rabbits. And then at the second year, we have 8. That's because on the inside we had 2. So 2 to the second is 4, and 4 times 2 is 8. So after 2 years, with the rabbit population doubling each year, we'll have a total of 8 rabbits in the population. So as you see, you go up and you see that it's a factor multiple of 2. So each time it's the whole population is increasing, is multiplied by 2 to get the population that we have after a certain amount of time. So having that, we're going to go edit some settings over here. We're going to have our population start at 2, which is what we said. And we're going to say our population goes up to, let's say 10. We're going to keep it small so then we could see actual jumps in behavior. And we're going to let the steps be 1. And for here, we're going to say CB1 so that the minimum rate would be that every year the population doubles, and we'll make this 5 to say that at most they make a litter of 5 rabbits a year, and the steps would also be 1. So having that done, we click done, and then we set up our graph for certain values. So we let the x-axis be -1, x be, let's say, a number like 10 for 10 years. Y is going to be our final population, so we're going to want to see a little bit of the below the graph so we don't get completely lost with the numbers on the x-axis. So we put -1, and on the top we're going to put a number like 50 to see. So we see this normal curve. So given that the not normal curve, this graph, that with the initial population of 2, which is right here, 0 and 2, so we know that at the 0th year we have initial of 2 rabbits, and then our population will be doubling in this case. So let's see what happens if we increase the amount of rabbits in the population. You see that over here at y equals 0, which is our y-axis, the value keeps going up, which makes the rest of the graph move up as well and to the left, which means that it's increasing rapidly, more faster than it would at lesser populations over time. So we notice that. So let's pause that, and we go back to 2. Now let's say we change the rate. So we're going to increase the rate from 1 to 2. You saw how the graph got more curved in, as you could say. So it moved a little bit more up, but it also moved closer to the y-axis, which shows us that the rate, the more we increase the rate, the more we're gonna have a jump in population over a small period of time. So noticing that if we increase the rate and if we increase the population, we're gonna have a more steeper slope, a more steeper graph, and this shows that that population when increasing and rate when increasing, you analyze and you see how it affects the graph, that as we increase these values, they tend to move closer to the y-axis and increase over time more rapid than other values. And if we lower them, they tend to go more away from the y-axis, more to the right and more downward. And that shows that as you increase these values, the amount will increase more faster than it would. So now, knowing this, I'm leaving it up to you guys to observe and analyze the behaviors in decay. So if we switch this, we have a value of this decay, and we will actually for C have values between 0 and less than 1, because if the value of C was 1, we would have a rate of change of nothing. So we start off with an initial amount, and we will have nothing after any type of time. So we'll have it from less than 0 to 1. So I'm going to leave that up to you guys. I showed you how to set this up, and now it's going to be your turn.